We tap our screens to send secure messages. We pull millions of database records in milliseconds. We hit undo without a second thought. It feels like magic. But beneath the slick interfaces, computers possess absolutely zero inherent intelligence. At their core, they are just machines violently shuttling pulses of raw electricity from one silicon gate to another. If left unguided, those electrical pulses would collide. Bank deposits would overwrite each other, and private messages would bleed into the wrong chat windows. The reason your digital life doesn't collapse into total chaos every time you open an app comes down to a single ancient mathematical contract: the function. A mathematical function is simply a strict rule. It takes items from an input space and maps them to an output space. Here, the left domain contains input values. Arrows map them to the codomain of outputs. But in the right image, input 5 splits into arrows to 4 and 7, breaking the mathematical contract. A true function guarantees one input yields exactly one single output. In computer science, this rule moves from the chalkboard to the compiler. When a software engineer writes an API endpoint to fetch a user profile or a database query to check your password, they are literally writing a mathematical function. The specific shape of this mathematical pipeline dictates everything. It determines whether your digital information survives intact, gets grouped together with other data, or is completely destroyed in the process. So, what actually happens to your information when a system intentionally funnels thousands of different inputs into the exact same output? In discrete mathematics, we call this a many-to-one function. It occurs when distinct input elements, let's call them A1 and A2, are mapped to the identical output value. Software uses this bottleneck by design. When a data scientist uses a classification algorithm to sort millions of distinct user behaviors into a single likely-to-buy category, or when an SQL database runs a group by operation to tally up daily sales, they are employing many-to-one functions. It is highly efficient for aggregating massive amounts of data. But there is a strict trade-off. Once those distinct inputs are merged into a single output, their individual uniqueness is permanently lost. For sensitive systems like banking networks or secure logins, overlapping inputs trigger catastrophic failures. This diagram illustrates the one-to-one or injective function. Every input on the left maps to its own distinct output. Panning to the second example, we see the failure state. Inputs x1 and x2 collide at output y1. The data's uniqueness is destroyed. By enforcing strict injectivity, developers can guarantee digital individuality. This mathematical rule is what generates unique user IDs for databases and ensures that your authentication token belongs exclusively to you. If injectivity protects the inputs, we have to ask a different question about the outputs. How do we build a system that guarantees no potential outcome is left empty or wasted? This diagram shows a surjective or onto function. If you look at the codomain on the right, every single possible value has at least one arrow pointing to it. Nothing is left blank. This concept is heavily utilized in systems architecture. A server load balancer operates as a surjective function, ensuring that incoming web traffic is distributed so that every single server in the rack receives data. Similarly, robust safety software is written to ensure every possible error code maps to a specific handling procedure. When a system needs to guarantee complete coverage and total operational efficiency, engineers rely entirely on surjective mapping. We now have a rule for perfect uniqueness and a rule for perfect coverage. What happens if an engineer builds a system that executes both simultaneously? This matrix shows the result in the top left quadrant. It's called a one-to-one correspondence, formally known as a bijective function. Every input has a unique output, and every output is covered. It creates a mathematically perfect mirror. The set of inputs and the set of outputs are locked in a flawless one-to-one pairing. Because no data is forced to compress, and no destination is left empty, the original state of the information is flawlessly preserved in transit. This perfect symmetry enables a rare mathematical property, the ability to run the machine in reverse. We call this the inverse function. It allows a system to take the final output and perfectly retrace its exact steps to recover the original input. F of x becomes x again. This specific mathematical reversibility is the exact mechanism that allows modern encryption to exist. When you purchase something online, a function scrambles your credit card data into seemingly random noise. It travels across the internet completely exposed. But because that initial scramble was bijective, the bank server can apply the exact inverse function to safely extract your original card number. It is the exact same mathematical principle that remembers your previous state, allowing you to hit the undo button on your keyboard and erase a mistake. The security of our private conversations, the memory of our applications, and the sheer scale of the digital economy don't rely on computers being inherently smart. They are entirely held together by the quiet, absolute rules of discrete mathematics, flawlessly mapping point A to point B.